The tropical systems actually allow a long wave approximation, especially for the ocean, which simplifies life quite a bit, even though its impact on modeling the interannual variability is not always very clear. What you do is, in this equation that we had before of the linearized version, we just set dv dt equal to 0, which means v, meridional perturbation velocity, just becomes a diagnostic. So you solve for u, and then you have to derive v as a diagnostic. It's not predicted from time variability. So in that case, you end up with a simple equation with the simplification of the Doppler shifted wave frequency in terms of the basic state and beta effect and the meridional mode and so on, with this complex coefficient here, can be simplified to just minus b beta k over k squared plus 2n plus 1 times beta over c. This is the long wave approximation. So in this case, you get reflections of low frequency, non-dispersive westward propagating waves. So then you take care of the reflection problem that we talked about. In this case, k squared is smaller, so you can further simplify this relation approximately to minus kc divided by 2n plus 1. So then you can look at the dispersion curves for a particular gravity wave speed. This is the low frequency detail of the dispersion diagram with the long wave approximation. Rossby waves are approximated as non-dispersive straight lines emanating from the origin as given by equation 6.75, which we looked at before. Like the Kelvin wave, the Rossby modes, here we call them ER star because they are long wave approximated. They are made non-dispersive because of this approximation, and the mixed Rossby gravity waves disappear in the long wave approximation. These approximate Rossby waves have phase speed and group speeds that are defined by this non-dispersive relation. Obviously d omega dk is 0 in that case. D omega dk becomes same as omega over k, so group and phase speeds are both the same as before, non-dispersive. So phase or group speed of the Kelvin wave is what you will end up getting. So here you are, the original waves we had with the mixed Rossby gravity wave, Kelvin wave, and the equatorial Rossby waves. With the long wave approximation for various meridional modes, you see that you get basically non-dispersive waves which are similar to the Kelvin waves. So if you imagine that forcing we saw before of piling up geopotential or mass at the dateline and letting it go and having Kelvin waves and Rossby waves, we can write easily the Kelvin wave speed and the Rossby wave speed in terms of the gravity wave speed, which is the Kelvin wave speed. So then the phase speed of the long wave long Rossby wave for various meridional modes become fractions of the phase speed of the Kelvin wave. Okay, this obviously simplifies life quite a bit, and in reality this turns out to be fairly realistic, in the sense we will see that in an El Nino case, when we look at the waves that we can extract from altimeter, which measures the sea surface height, then we will see that actually Kelvin wave is about 3 times faster than the Rossby wave, which is consistent with the long wave approximation. And the reflections at the eastern boundary produced based on the frequency of the Kelvin wave, either coastal Kelvin waves or eastward Rossby waves, or both. So the energy gets split into westward Rossby waves and coastal Kelvin waves. Okay, so there are 2 criteria that we looked for the reflected waves. First, it must have the same frequency as the incident Kelvin wave. Secondly, it must have a group velocity away from the boundary. In this case, of course, from the eastern boundary towards the west, in order to carry the reflected energy away from the boundary. Okay. In this reflection process, I'm missing omega here. Frequency is the independent variable. So the reflection at the eastern boundary is very specific for the ocean. Western boundary is no problem because you can produce short Rossby waves and Kelvin waves which have eastward group speeds going away from the boundary, whereas in the eastern boundary it's a little bit more complicated. So I will leave this here and conclude again with what we started with at the beginning in terms of the summary of the results that we looked at in this chapter. Okay, I hope it's all clear. Just deriving the dispersion diagrams for the atmospheric wave, looking for a family of waves with specific solutions for various basic states, and including meridional shear, and then look at real shear and look at the impact of the depth, the length scale in the horizontal, and the what else was affecting the equatorial trapping? The length, the depth, and of course the background state. And we looked at the equatorial trapping mechanism in terms of the induced vorticity, and we said the exponential decay of the vorticity with latitude is the fundamental thing for equatorial trapping process. Okay, as soon as you move in latitude, you're going to have induced vorticity because of beta. So beta is the constraining force, and anything that changes the equatorial trapping is going to change the beta effect essentially, right? Stronger beta effect gives you stronger trapping, and weakened beta effect is going to give us weaker trapping. That's all.